Previous few lectures, we have discussed about different aspects of HMMs and the different problems associated with HMMs. Now we will be discussing about one of the most important problems. How do we learn the parameters of HMM? Just to recall, the parameters of the HMM are this pi, a and phi, where pi stands for the prior probability, the probability of starting in state z I z1 equal to either one of the k states, transition probability matrix A, which tells us the probability of transitioning from a state j to a state k, and an emission matrix or an emission factor phi, which tells about the probability of observing different symbols or different observations given the current state that we are in. Now, when we talk about parameter learning for HMMs, there could be two cases. The first case, which we call as the fully observed case, where the hidden state sequences are known to us. So that is Z1, Z2 till Z capital T is known to us. And we now want to learn the parameters. As you might expect, this case is significantly easier than the case when the hidden state sequence is unknown to us, right? So we'll look at that after finishing the case for fully observed data. And now we'll be trying to solve this or learn parameters given this data set D, which contains n sequences. So this n sequences where the first sequence is Z11, Z12 through Z1, T1, and correspondingly the observations are x11, x12 till x1 and capital T1. So here the first number corresponding to is shown in the subscript tells us the sequence number, and the second is the position within that sequence. We have n such sequences, and we are also saying that these different sequences could be all of different lengths. So this is another interesting property which HMM-like algorithms allow us to play with this kind of data, which is very common. For example, if you're recording the audio of someone speaking something, you may or may not get the audio of equal length. For most of the other algorithms that we had seen, the data was a fixed number of features, but now you can have variable length time series. But this is where HMMs come into their own. You can still be able to learn the parameters and predict even for uneven or different length time sequences. So each of the Ti here could be of a different length. Before we go into talking about learning for all of these different sequences, let's try to first simplify this problem and see how can we go about learning the parameters. So before we go ahead, could you think of one principle that we have seen thus far in many of our previous algorithms which we could leverage here to learn the parameters? So if your idea or if your thought process was use MLE, then you're on the right track. So now we'll be discussing how do we find the likelihood of a sequence Z1 through T. It's a single sequence that we are currently talking about. So you might have remembered if you try to write the likelihood based on our previous discussion, you might write it as for the first hidden state, or for the not the hidden state in this case. It's a hidden state, but it's observed. For the first hidden state, the probability. So we're trying to basically just writing the joint probability given the parameters theta, joint probability of the observation the state sequence Z1 through T. So that is given by pi of Z1 times the transition from Z1 to Z2. So the hidden state at time 1 to hidden state at time 2, so on till the hidden state at time capital T minus 1 to the hidden state at time Z of ZT at time T. Now we will be writing pi of Z1 in a format which is going to be more conducive for further calculations. So we want to write pi of Z1 in terms of J, because you could be in any of the jth state, right? Where j belongs to 1 through k. Could you take a minute and try to write pi of z1 in a convenient format? If you're thinking about how to go about writing, so remember how we wrote the likelihood or how we calculated the likelihood in the case of logistic regression when we are trying to figure out when we were trying deriving the cost function, or how we wrote the formula for Bernoulli likelihood when we were talking about coin tossing. So we should be trying to think in those manners. So we could be writing, firstly, pi is a vector of length k, where x1 equal to j is the probability that the first state would be, so at the first time instance, the state would be j. Right? So we could write pi of z1 is pi j, which tells the jth entry in this vector if z1 equal to j. Right? So it is this line, this expression, that we want to somehow write in terms of something more convenient, more mathematically convenient. So previously we have seen, mathematically more convenient forms could be either a multiplication over all the j's ranging from 1 through k, or some form of summation. So what we'll do is to write pi of z1 as a product of this quantity, which is pi j raised to power identity over z1 equal to j, right? So only in the case when z1 is the actual state, right? When z1 is the j, which is the observation of the state sequence that we have seen at time t equal to 1, only in that case identity function I z1 equal to j would return 1, otherwise it would return a 0. So for all the other j's for which this returns a 0, you're only raising something to the power 0 and then taking a product over all these quantities. So all of those products would be 1 times pi j raised to power 1, right? Where j is the actual state in which z1 is starting at. Right? So this is a convenient way to write down this expression. We'll see later why this becomes a very useful way to write this expression. Now the other thing that we want to write is the terms involving the transition matrix. So could we write a z1 z2 in a more convenient fashion, in a similar fashion that we have written down pi z1? Take a minute and try to write in terms of something similar. The only thing that you might see different is now z1 z2 would be, you have two different states and both of them could be in two different, so you have states at two different time steps. So they could be, you'll have to, instead of having this identity involving only one variable, you'll have to involve it over multiple two variables in this case. So if we have to write a z1 z2 in terms of j comma k, where both of them belong to 1 through capital K, we could write it as a product of ajk raised to power identity where z1 is j and z2 equal to k are again the actual states, and this is multiplied over all j's and all k's. So again, you can convince yourself that only when z1 is the correct state and z2 is the state that we are observing, so only for those j and k values will you get the identity function to return a 1, otherwise you will get the identity to return a 0. So in those cases, you're raising something to the power of 0, you'll get product of all ones except for the ajk term. So a z1 z2 would basically be ajk, since z1 is j and z2 is equal to k. So we have written down the whole thing in a more mathematically convenient fashion. Now, if you notice that there is this product of these multiple terms, a z1 z2, a zt minus 1 through zt. So could you now write the product of all of those terms in a more convenient form, you can leverage the above formula that we've written for A, Z1, Z2 and try to generalize it across time. So you can thus write it as A Z1 Z2 and the product till A ZT minus 1 comma ZT. So this product is first over the timestamps from t equal to 2 to capital T, and then you look for different pairs. So this timestamp is basically telling us ZT equal to K and ZT minus 1 equal to J. So this expression that you see is fairly similar to the expression that we have seen earlier for A Z1 Z2. All we're doing is to, instead of just Z1 Z2, write this expression for all ZT and ZT plus 1 or ZT minus 1 and ZT, right? So if you go this way, you'd be able to write this in a much more succinct fashion. So thus far we have written the likelihood as, this two different terms, and ideally what we want to do is to find out the logarithmic of likelihood. That again makes a lot of sense here because you have a lot of these products. Log will transform them to sums, which is useful. First, it's easier to solve. Secondly, it would also involve ensuring that you're preventing the underflow, numerical underflow error, because you're multiplying a lot of probability like terms or a lot of terms which are going to be less than equal to 1. So if we write the log likelihood of this expression, so logarithmic of the likelihood, we can write it as the logarithmic of these two terms which are shown in the blue and the yellow shade. This is essentially what we've seen in the previous slide. So I've just rewritten them again on this slide. And I'm going to call this first term as F and the second term as G, so that we can solve both of these independently. Now, just leveraging that logarithmic of F times G is logarithmic of F plus log of G, we can further simplify and solve and try to reduce this into something more convenient for us. So let's try to write now logarithmic of F in a more simpler fashion. Could you take a minute and try to write it yourself? Okay, so all I'm going to do is to just expand this out, this term F, over all the different J's. I'm just going to write it for J equal to 1, J equal to 2, so on and so forth. So as you can see, it's a product of pi 1 identity Z1 equal to 1, pi 2 identity Z1 equal to 2, so on and so forth till pi capital K, I Z1 equal to K. It's a product of capital K terms and a product. So since you're talking about logarithmic of products, you could transform that into some of the logarithmics of each of these terms. So this can be written as identity of Z1 equal to 1. We get that because it's pi 1 raised to power identity identity Z1 equal to 1. So logarithmic of something raised to the power something, let's say pi 1 raised to power something, that something will come in front of the logarithmic. So we have basically now written identity of Z1 equal to 1, logarithmic of pi 1 plus the other terms which look fairly similar. If you have to write in terms of summation, it's summation of J equal to 1 through capital K, identity Z1 equal to J multiplied by logarithmic of pi J. So could you take a minute and try to write something similar for the G term? Can you write down logarithmic of G? It has to be written in a fairly similar fashion. So you have to just convert the products into summations. Okay, so I've written logarithmic of G as logarithmic of, so all I've done is to just firstly expand out over the dimension t. So I've written this expression for different t's. If you notice, I firstly put for t equal to 1, so you get identity of x1 equal to j and x2 equal to k. And similarly, if I write it for the entire expression, I'll get a product of t different terms like this. So that is a summation. And since it's a product of t different terms and you apply logarithmic on them, you can write it in terms of summation of the logarithmic of these t different terms. And if you further expand over j and k, you can write it as a triple summation. So triple product will get converted to a triple summation. And since ajk was raised to the power identity x t equal to k and x t minus 1 equal to j, so that term also comes out, and then you finally are left with logarithmic of ajk multiplied by the identity term. So this is how we've written logarithmic of j. We've also written logarithmic of f, logarithmic of g, right? So at this point of time, all you need to do is to just maximize this function, and you can get an estimate for the MLA estimate for ajk and for pi j, right? So that is going to be pi hat of j and a hat of jk. I'm not going to do the derivation. I would request you to try it at your own time. But what I'll do is to now get back to the problem of n sequences that we were discussing before. So this log likelihood that we've written is for one sequence. This can be very easily generalized to multiple sequences, and that is what I'm going to do now. And let's get to now the n sequences problem. So we can now write now what we want to do is to estimate pi and a given this data, right? So in this data, if you notice, I'm not talking about the observed data for now. I'm only talking about pi and a, because these are the two parameters you could learn just using the observed state sequences. You don't need the observation data x's for learning pi and a in this case, right? So I could write down the logarithmic of the probability of this data given the parameters a and pi as so that would be the log likelihood over this multiple different sequences, right? Or the log likelihood of the data given the parameters. So different sequences means different samples or different, so samples that in the traditional sense of machine learning that we'd be seeing. So we could write this as the summation over, since you're applying this log likelihood over different sequences, and zi is the ith sequence, you could just apply the logarithmic applied over the product of these different sequences. It's just the summation of the logarithmic of these terms. And I'll be now writing down two quantities which might seem like magic for now, but we'll get to them in a minute, and you'll see that this looks like very common sense numbers to compute for computing the MLE or getting the MLE solution. So the first term I've written is n superscript 1 subscript j, which is summation over I equal to 1 to n. So I equal to 1 to n means the n sequences that we have. And this is the identity over z I1 equal to j, right? So let's try and see what this could mean. So this is the count of the sequences where z1 equal to j, right? So if z I1 equal to j and the identity over that is 1, that means that for that particular sequence, the first state is j, right? So we are basically writing down this summation over the different sequences. We'll thus get the count of sequences where z1 equal to j, right? But then in the bottom, I've written another function or another count, n subscript jk, where I'm first doing a count over the different sequences. which is I equal to 1 through n. And then for each of the sequence, I am doing a count over all the timestamps. So notice that for the ith sequence, you can have capital T underscore I timestamps. They may or may not be equal across different sequences. And here I've written the identity over xi comma t equal to j and xi comma t plus 1 equal to k. So could you think what this summation would give us? So this summation is giving us the count of transitions where at time t you were at in the jth state and at time t plus 1 you are in the kth state, right? So you're doing this summation, this counting over one sequence first. So that's the inner summation. And then you're doing this across all of the sequences, right? So this is telling you that across all the total number of sequences, how many transitions do we see from state J to state K, right? So using these two numbers, could you think what the MLE solution for pi of j and a of jk could be? Think for a minute. So it's fairly intuitive at this point of time to see that the MLE estimate for pi hat of j, or the prior probability, is the ratio of n superscript 1 subscript j divided by the summation of n superscript 1 subscript j over all different j's, right? So if you notice, n superscript 1 subscript j is the count of sequences where z1 equal to j, where you're starting in the jth state, right? But you could start in any one of j equal to 1 through capital K states. So the ratio of that gives us the probability of starting in the jth state. That's it. So you could have thought about this even without having worked out the entire log likelihood formulation. So, but that's the whole point about MLEs, that it often matches common sense. Similarly, a hat of jk, so which is the transition matrix value at j and k, which is telling us the what is the transition probability from going from state j to state k. That is going to be the count of transitions from j to k divided by all the transitions, the count of the transitions from state j to any of the state k, right? So basically the denominator is telling that how many times did you visit state j, right? You could have visited state j and you could have moved to some other state, right, apart from k, right? So both of these quantities ensure that these estimates are normalized, right? So we've seen how to estimate the prior probability and the transition matrix. How do we determine how to estimate phi? Could you think for a minute? So the basic idea behind estimating phi firstly involves understanding what phi tells you, what phi represents. So is the observation sequence multinomially distributed or is it normally distributed? So based on that, we can calculate the parameters. So the case one, we consider the multinomial emission. That is, we are writing phi of JL as the probability that you're observing the Lth symbol. So we have been talking about this example where we're observing heads and tails, right? So there we have two symbols in the observations and zt equal to j. So at time t, you are in the jth state and you're emitting the Lth symbol, right? Where L could be from 1 through capital L. So on similar lines, we can write down the formulation for phi hat of JL So this we write as n superscript x subscript jl divided by nj. So where n superscript x jl is the count of the number of times where you are emitting L, right, when you were in the jth state, right? So let me repeat that again. The count over all the sequences and all the timestamps in each of the sequence when you observe Lth symbol when the state was J, right? So that count divided by Nj, where Nj we have discussed earlier is the same as this quantity which we used to estimate a hat of jk, the denominator of that. How many times were you in state j? So effectively what phi hat of jl is telling you is out of all the times that you were in state j, what was the proportion of times that you emitted the Lth symbol, right? Could we do something similar for when phi is normally distributed? Could you think for a minute and tell me what you think could be mu hat of k and covariance or big sigma hat of k? So mu hat of k, as you might expect, is xk bar over nk. But what is xk bar? So xk bar, as I've written in this formulation, is telling you it's basically the sum of all of the observations x's when you are in the kth state over all the timestamps and over all the sequences n, right? So each time you're in the kth state, you add you add the observation to a sum starting from sum equal to 0 and you divide that by nk, right? Nk is the number of times you were in the kth state. So again, as you would expect, mu hat of k is the sum of all the observations when you were in the kth state divided by the number of times you were in the kth state. On similar lines is the formulation for covariance sigma hat of k, which is given by this term xx bar transpose k minus nk times mu hat k times mu hat k transpose divided by nk. This might look a little confusing, but let's again try to see what xx bar transpose k is, this term on the top. So this equals to xit multiplied by xit transpose each time you are in the kth state, right? So if this formula looks confusing, it is good to go to the Wikipedia page and let's look at the formula for variance, right? So you have the formula for variance as pi xi squared minus mu squared, right? So this formula is fairly similar to the formula that we are seeing thus far. So you have mu squared, right? Mu squared into nk divided by nk, which is just in some sense mu squared, and you have an x squared kind of a term, right? X squared kind of a term by nk, which is effectively xi squared term multiplied by a pi term, which in this case is 1 over n. Okay, so far so good. Let's try to work out a very simple example and try to learn the parameters for this case. So I have 3 different sequences. In this case, I've kept them to be of the same length, but you could very well have examples where you could have different sequence lengths. Could you tell me what is pi hat, a hat, and phi hat for this case? Think for a minute. Go back to the previous slide and see if you need to revise the formulation. But even if you don't remember the formulation, you should be trying to think out aloud from scratch that what you would have as phi hat, a hat, and phi hat. Okay, so the first thing first, we first want to calculate n superscript 1 subscript j, which is telling us the number of times zj would occur at time t equal to 1, right? So we calculate this term as summation. Oh, there's a summation which I've missed over here. Summation over identity of zi 1 equal to j. So which is basically telling us that for each of the jth state, how many times is it occurring over the different sequences, right? So you can see that bias occurs in the first state twice and fair occurs once in sequence 2, right? So n1b is 2 and n1f is 1, right? So then based on this data, we can write pi hat equal to pi hat of b comma pi hat of f, where pi hat of b is the number of times you start in state b divided by the total number of times or total number of sequences that you have, so 2 by 3. And similarly, pi hat of f is 1 over 3, right? So again, if you see, it's fairly obvious. You just do the simple raw calculations to see what could be the parameters. On similar lines, we can calculate the transition matrix A. So first we're going to look at the count of the transitions from any state j to any state k, right? So that's the most general term that we're trying to define, n sub j k, right? So what could be the values of j and k? In this case, you could have j varying from either bias or fair and k also varying from bias to fair. So in total, you will have to we want to calculate 4 such counts. So the first thing I'm showing here is the counts from bias to bias state, and I've shown them in this yellow color. So there are 3 such counts of going from bias to bias, right? And in blue, I have shown the transitions from bias to fair state. There is only one such transition, and the transitions from F to F, fair to fair, I have shown in this light red. So you can see that this is spanning multiple different sequences. In this sequence, we have 3 such transitions, and in this sequence, we have 1 such transition. And the number of transitions of going from fair to bias is 1. So having given these numbers, could you think about what would be A, BB, ABF, AFF, and AFB? So A hat BB, we're going to be writing as the number of times you were in state B and made a transition to state B divided by the number of times you were in state B, right? So the number of times you were in state B made a transition to state B is NBB. The number of times you were in state B and made a transition to B is NBB, and the number of times you were in state B made a transition to state F is NBF. Right? So this quantity turns out to be 3 by 4. Similarly, we can calculate A hat of BF, which you don't need to even calculate in this case, given that you have only 2 possible states. So it's fairly obvious that it would be 1 minus A hat of BB, so it would be 1 over 4. Similarly, A hat of FB would be the number of transitions from F to B divided by the number of times you're in state F. So that would be 4 over 4 plus 1, or FB would be 1 over 1 plus 4, 0.2, and FF would be 4 over 4 plus 1, 0.8. Right? And now coming to the final set of parameters that we want to learn, which is phi. So how many parameters in the phi matrix do you think we need to learn? We have 2 observation symbols, head or tail, and we have 2 different states, bias or fair. So in total, we'll be having 4 parameters that we want to learn here. phi hat of BH, observing H when you're in the bias state, observing tail when you're in the bias state, which is phi hat of BT, and similarly phi hat of FH and phi hat of FT. Right. Could you think for a minute and tell what phi hat of BH would be? Phi hat of BH would be the count of the times you were in the bias state, observed heads, divided by the number by the count of the times you were in the bias state, right? So, which is I've shown in this violet purplish color that I've shown the count of observing a head when you're in the B state, bias state. So you have, out of the times you were in the bias state, out of the 1, 2, 3, 4, 5, 6 times you're in the, out of the 6 times you are in the B state, 5 times out of that you observe heads, and 1 time out of that you observe a tail. So this number is written wrongly in this case. It should be 5 over 6, and phi hat of BT would be 1 over 6. Right? So once out of the 6 times that you're in the bias state, only once have you observed a tail. Similarly, we can calculate phi hat of FH and phi hat of FT. Right. So with this, I'll end this video, and the last part, which is going to be coming up next, we'll be doing parameter estimation or parameter learning when we do not have fully observed data. That is when we don't know about the state sequence ZI.